Welcome to this 17th lecture in Physics 10 in 30 lectures. We continue our coverage of thermodynamics in Chapter 8, finally looking at what makes this thermodynamics, heat engines. We start with the second half of the overview, going over the laws of thermodynamics and heat engine cycles covered in the textbook. And because you will see certain thermodynamic processes referred by their names, isobaric, isochoric, isothermal, and adiabatic processes, we talk about how each of these processes are constrained and how each constraint simplifies the thermodynamics problem solving with each named process. Then, we have a mix of conceptual lectures borrowed from Physics 4B and the old recordings created for this class. First, Work and Internal Energy is a lecture snippet we are borrowing from Physics 4B to illustrate the consistency between the first law and our model of kinetic theory of gas. We also have the fire syringe demo in this lecture. In Heat Engines and Efficiency, I go over the textbook's coverage of first and second laws of thermodynamics using the examples of heat engine cycles in the textbook. Then in Calculations with the first law, heat engine efficiency, I go over a couple of number questions involving heat engines. Also, there is a recorded demonstration of a working Stirling engine at the end of the section. And finally, we finish with the two borrowed lecture clips from Physics 4B, Waste Heat and a Perfect Engine, and Disorder, Entropy, and Second Law. They are mostly done conceptually, so I encourage you to give them a watch, although for the purpose of homework questions you will see this week, you only need the materials through Calculations with First Law, Heat Engine Efficiency. Let's start with the overview, part 2. Oh, and a reminder for all the Physics 10 recorded lectures, the chapter and section numbers in the video are shifted from the chapter and section numbers in the LibreText version of the textbook. Please look at the chapter and section headings to match the videos up to the correct part of the textbook. Hi, this is Chapter 8 Overview, Part 2, covering the laws of thermodynamics and discussing some things having to do with the heat engines. So, the laws of thermodynamics. Now, in section 8.8, we start out with the first law. But there was something called the 0th law of thermodynamics that was mentioned way earlier in section 8.2 temperature. And this is something that you might have assumed that things come to thermal equilibrium when two things of different temperatures touch over a long enough time, they come to the same temperature. So 0th law defines the thermal equilibrium. I guess my perspective on all the laws of thermodynamics is they all kind of simply restate something that we already knew. Like the first law, it states the conservation of energy. Or it states something that's like a logical tautology, or something that you would have assumed was true if no one told you about it. But I think they are important as a reminder of things that govern the thermodynamic processes you will see. So the 0th law, in case there was any doubt, things come to thermal equilibrium. That's sort of the spontaneous process that happens. And the first law of thermodynamics, which is what section 8.8 and some degree section 8.9 covers, it states the conservation of energy, which we have been dealing with in mechanics 2. Now, when we are dealing with the mechanics, we talked about conservation of mechanical energy, and then anytime there was an apparent violation of mechanical energy, we said that energy goes to heat. It's still conserved in the overall sense. It's just not mechanical energy. Now, first law of thermodynamics gets explicit about it. So it says change in internal energy, which includes all forms of energy and especially the thermal energy. The first law of thermodynamics says that that change could come from two sources. One is the mechanical work, the kind of mechanical energy that we've been dealing with before, or heat transfer, the transfer of thermal energy. And I should point out this minus sign here. So if you have seen first law of thermodynamics, for example, in a chemistry class, you might have seen this as a positive plus sign. The reason our version has a minus sign has to do with the definition of the symbol W. When we use the symbol W, what we are talking about is the work done by the system. So as the system does work on the surrounding, the energy leaves the system. That's why there's a minus sign here. If the system is doing positive work on the surrounding, that reduces your internal energy. In chemistry, I believe whenever they use a symbol like that W or work without specifying the details, they're talking about the work being done on the system. So the work being done transfers energy into the system. So in this class, so first law of thermodynamics says change in internal energy is given by net heat transfer into the system. So if it's net heat transfer out, this Q will be minus. So net heat transfer into the system minus work done by the system onto the surrounding. And in section 8.9, we also talk about thermodynamic processes. It looks like that's not covered in any of these branches of this mind map. For some reason, Notebook LM just didn't include it. I'll do a separate lecture video talking about the 4 named thermodynamic processes. We don't do much quantitative calculation with them, but I think it's still good for you to know the names and the definitions of those named thermodynamic processes. Section 8.10 introduces the second law of thermodynamics, and I guess it starts to get mentioned, hinted at, as we talk about the reversible processes or the irreversibility of the processes. Sometimes people refer to the second law of thermodynamics poetically as the arrow of time, as it's the only law of physics that actually refers to some possibility of irreversibility of processes. It's the only law of physics that we know that lets you tell if a video that you recorded of some process is running backward instead of forward. All the laws we covered in mechanics, like conservation laws, they describe processes that could be happening in one direction or the other direction. If you recorded a video backward, based on conservation of energy and momentum alone, you wouldn't be able to tell if the process was running forward or backward. But with the second law, we talk about spontaneous processes, that heat flows spontaneously only from hot to cold. So if you see heat flowing from cold to hot, you can tell, oh, the time must be running backward. And second law is also unique among the laws of physics you might hear, in that you will see multiple different statements of second law. So in section 8.10, one of the statements of second law you will see is that second law says 100% efficient heat engine isn't possible. That if you build a device that's going to convert a flow of heat into mechanical work, that turning that 100% of input heat into mechanical work isn't possible. That some of the input heat has to go out as quote-unquote waste heat. And I'll share a borrowed video from Physics 4B to talk a little bit more about second law and its sort of a fundamental statement. I do think those are related to what's in your sections 8.13 and 8.14. But with those sections, we don't do anything quantitative. It's mentioned more as a interesting thing for you to have heard of, but don't worry about understanding every single detail. Now, we are talking about the heat engine efficiency. So let me open this heat engines and applications branch of this mind map. So now efficiency. I think we introduced the definition of efficiency in section 8.10 alongside the second law of thermodynamics. And when it comes to heat engines, we define their efficiency as the mechanical work output divided by heat input. This comes from a more general sense of efficiency, which I would state as what you want divided by what you pay. So something that has 100% efficiency would give you basically 1-to-1 ratio of what you've been wanting to what you have to pay. Now, in later applications of heat engine cycles, you will see where efficiency is more than 100%. In those circumstances, we usually talk about like coefficient of performance. I think it's a little bit jarring to most people to hear about efficiency that's bigger than 100%. In fact, when it comes to heat engines, there's something called the Carnot efficiency that's based on the Carnot heat engine cycle, a highly idealized, almost impossibly idealized cycle. And Carnot efficiency, which we are saying is maximum theoretical possible efficiency, it's not 100%. It's determined by available temperature, thermal reservoirs, high temperature reservoir and low temperature reservoir. And the Carnot efficiency that you would calculate as, I guess, the 1 minus the ratio of the low temperature to high temperature. It's less than 100%. And you can give another statement of second law of thermodynamics from that, saying the maximum possible of any imaginable heat engine cycle is the Carnot efficiency given the extreme temperatures available in the hot thermal reservoir and the cold thermal reservoir. And we do talk about other heat engine cycles. I guess in my physics 4B, I talk about 4 heat engine cycles total. Here, we are not trying to be comprehensive in our coverage of heat engine cycles. So we do mention Otto. It's named after some German guy. Otto cycle. It's the cycle for the internal combustion engine, like one in your automobile, spelled auto differently. And I guess in my other class, I do cover diesel cycle and something called the Stirling cycle. Because our coverage of heat engine cycles are somewhat schematic, we don't go into those details. I do have a working demo of a Stirling engine that you will see as part of one of the later lecture videos. I think the homework calculation video, at the end of it, you will see the Stirling engine demo. And some of the most important examples of applications of thermodynamics is the heat pumps and the refrigerators. So by heat pumps, we could mean 2 different things. It could mean a device that heats your home, makes your home warmer by pumping heat from the colder outside to the warmer inside. That's not a spontaneous process that happens, Second law of thermodynamics. Heat spontaneously flows from hot to cold, not cold to hot. But heat pumps are not spontaneous things. You have to put work in to get them to operate. So with the heat pumps, you can pump heat from the low temperature to high temperature. And areas with milder winters, like the Bay Area, you might have a heat pump at your home because it's at these milder, not so cold temperatures where heat pumps are at their most efficient. In fact, it's in this context where we talk about coefficient of performance because in the ideal circumstances, the amount of heat you can pump into your home using some electrical mechanical energy, it's several times the amount of mechanical work you have to put in. So if you have like a portable heater, sometimes people say, oh, those are quote unquote 100% efficient because all the electrical energy turns into heat. Well, that's the lowest efficient heating device can be. They can be actually more efficient with something like a heat pump. Now, if you turn the heat pump around, instead of having the colder side be outside, have the colder side be inside and the warmer side be outside. That's your air conditioner. When outside is hotter, you can use a heat pump with the direction reversed to keep the inside colder than the hotter outside. The operational principle is the same. You are pumping heat from the colder, this time inside, to the outside. And the calculation for the coefficient of performance there is different because it comes down to what is the quantity that you want. So with a heat pump, the quantity that you want was the heat being delivered into your home. And with the air conditioner, reverse the heat pump, the quantity that you want is the heat being removed from the lower temperature reservoir, which is your inside. So the formula for coefficient of performance for heat pump and air conditioner looks a little bit different. I think the formula that we use for the air conditioner is the same one that we've used for refrigerator. And refrigerators, the society looked different from before the widespread use of refrigeration versus not. The kinds of foods you are able to eat, it's driven by availability of refrigeration. And this is all possible due to our understanding of thermodynamics. So I think that's everything. As I said, I will make a separate video talking about the 4 named thermodynamic processes, because I don't see them mentioned anywhere in this mind map. Those named thermodynamic processes are covered in section 8.9, the First Law of Thermodynamics and Heat Engine Processes. And again, your textbook goes a little bit more into Second Law of Thermodynamics than they were covered in this branch of the mind map. I will share some borrowed lecture videos from Physics 4B that kind of corresponds to what your textbook talks about in sections 8.13 and 8.14. Now, we will start out the video about the 4 named thermodynamic processes. In this video, we will look at the 4 key thermodynamic processes, or the 4 named thermodynamic processes. They are named because they are key, they are important, they are useful. There are other thermodynamic processes, but they are not named because they are not as useful. Now, having highlighted their usefulness, I do have to confess that in this conceptual physics class, we won't quite use them as much in quantitative problem solving, because that's more of a calculus-based physics material. But I thought it would still be good for you to know the names of these processes. For those of you who may be taking general physics later, this will be the first time you will have seen them, and you will see them again later in your future class. So let me start out with these 2 isobaric and isochoric processes. If you know a little bit of Greek, they are what they sound like. Isobaric means same baric. I think baros means weight. And in modern terms, it ends up being constant pressure. You can see it illustrated in this PV, pressure volume diagram. You can see that throughout the process, the pressure isn't changing. And this simplifies this. If we have to calculate work done during this process, the definition of work in thermodynamic context involving fluids, usually gas, is work is pressure times a change of volume. And when the pressure is constant, this calculation is really simple. You just calculate the constant pressure times the final volume here, that would be V2, minus V1. And that gives you this area under the curve. And if you have to calculate it, you can look at it like your height is the pressure, your base is the change of volume, and you are simply calculating area of a rectangle, height times base. Now, it's not quite simple in other ways, but it is really simple if all you want to do is calculate the work done during an isobaric process. Isochoric process is similar. Isochoric, I think this portion comes from word meaning like space, place in Greek. And in modern terms, it ends up meaning constant volume. Sometimes you might hear the phrase isovolumetric. I don't like that phrase just because, iso or isos is Greek and volumetric is Latin. I don't like mixing etymologies, but some other people do. So with the isochoric process, it happens at constant volume. So if we are thinking of the amount of work being done, then pressure times the change of volume. The change of volume is zero, so no work is done in isochoric processes. It's like applying force with no displacement. You need displacement for work to be done, so no work. Now you might wonder then, what is this process useful for? What is changing? I guess I can highlight what this means. So far we've been talking about pressure and volume, which with the temperature can be related to the ideal gas law that you have seen, PV equals NKT. And one of the new things that we are covering in the second half of chapter 8 is the first law of thermodynamics, which says that change of internal energy characterized by microscopic kinetic energy and I guess potential energy as illustrated in the latent heat. That change of internal energy, that there can be two sources of change of internal energy. It could change by transfer of thermal energy, so Q, net heat transfer into the system. I think so far that is intuitive. And the dynamical part is you can also have energy change the usual way, the way it was happening in mechanics too, through work being done. So if W represents the work being done by the system on the surrounding, then the change of internal energy is net heat transfer minus the work done by the system on surrounding. So with the isochoric process, no work is done. So in terms of change of energy, there's not going to be change of energy due to work being done, but you still have transfer of heat. So with the isochoric process, the thing that's being made simple is however much amount of heat you transfer, that becomes your internal energy. And in fact, that's the sense in which isobaric process is a little bit more complicated. Because when you look at the change of internal energy, there's going to be work being done, as you see in this PV diagram with this non-zero area, and there's going to be heat transferred. And figuring out exactly how much heat is transferred in isobaric process, it takes a couple additional steps, which we won't do and I won't refer to here. So this is the isobaric and isochoric process. They are illustrated best on this PV diagram, and the way in which these constraints simplify the process is also demonstrated on the PV diagram. Now, our next two and the last two named processes are isothermal and adiabatic processes, and I think they require a little bit more thinking through to see what is being simplified. But just as a matter of definition, isothermal means constant temperature. And I do have to caution you. I think sometimes when people see this word, they think of thermos, because I guess there's this word therm, and they think of insulated. And what I will tell you is, in case of isothermal process, it's almost like the exact opposite of what you are thinking of. In order to have constant temperature, this system that we are working with is not insulated. In fact, it's the opposite of insulated. It's exchanging heat with its surroundings so well that allows it to maintain the same temperature as its surrounding. That's what isothermal means. If you want to think of insulated, what you want is actually adiabatic. It does mean just no heat transfer. That's the definition of adiabatic process. In an adiabatic process, no heat transfer has occurred. And one of the ways in which that can happen is that this is well insulated. So no heat transfer between inside and outside. So Q equals 0, then that means the process will be adiabatic. There are other ways to make a process adiabatic, but let me talk about that with the diagrams on the lower half. Especially because I think as you look at this PV diagram here for isothermal and this PV diagram for adiabatic, you might feel like they look the same, kind of curve that goes, like something that might look like 1 over x, or I guess 1 over v, and that sort of looks like that. And let me use the explanations and graphics on the lower half to kind of distinguish them. So the isothermal process, it's described here with some more detail. Isothermal maintains constant temperature. That is what isothermal means here. And with that first law of thermodynamics, that means some interesting results. With the first law saying the change of internal energy is the heat transfer minus the work done by system. I guess what I have to tell you is that temperature, it's related to the internal energy. And in fact, if we are talking about the gaseous system like ideal gas, temperature is proportional to internal energy. So when your temperature doesn't change, that means your change of internal energy is 0. And with that, on the right hand side here, if this whole thing is 0, then it must mean that the net work being done by the system is equal to the net heat transfer. And that's what this is saying. Work done is equal to the transfer of heat. So if you have an isothermal system, and if somehow you know how much heat was transferred during the process, then you can get work done just directly from that. I think in general physics class, it's often more easier to calculate the work being done. Now, you do need a calculus to do that, to figure out this area. It's not a simple geometric shape. But once you figure out the work being done by calculating this area, that immediately gives you the heat transferred. This is a contrast from the isobaric process. In an isobaric process, when you had the work being done by the system, that wasn't automatically equal to the net heat transfer because there was also change of internal energy that comes from this volume expansion with the same pressure. So that's an isothermal process. It means constant temperature, and that implies some things. And I guess here it says it must occur slowly. Yeah, it must occur slowly enough. It must occur slowly enough that whatever the temperature inside is equal to the temperature outside. One of the ways you'll do that is by making sure this material can conduct heat well. Then that'll make it easier to keep the inside temperature same as outside. And you make the process occur slowly enough that the amount of heat that can be transferred, that's enough to keep inside and outside in thermal equilibrium. So usually slow processes, that's what isothermal means, usually. Now for adiabatic process, we'll come back to that chart. For the adiabatic process, again, it involves no heat transfer. Q is 0. And that can happen a couple different ways, or a combination of two ways. One is you could make the wall well insulating so that any heat transfer that occurs slowly enough, like close to 0. Now, in those processes, if it takes a long time for the process to happen, so any realistic material, there's going to be some heat conduction, if nothing else, even radiation will be occurring. So in order to make sure this heat transfer is as close to 0 as possible, the process has to happen rapidly, so that at the end of the process, the amount of heat transferred is negligible. In fact, you see me doing a demo with something called a fire syringe in the lecture, going over the work done and internal energy. And the way I make sure the process that occurs is like an adiabatic compression, is I compress the piston really rapidly. That way, any heat that's being conducted to the surrounding, it's negligible. So again, in adiabatic process, there is no heat transfer, and that means something according to the first law of thermodynamics. Change of internal energy, or delta U, is equal to net heat transfer minus work done being by the system. So from the definition, no heat transfer. That means whatever change of internal energy there is, that's minus of the work being done by the system. So in an expansion like this, where the system is doing positive work, there's a change of temperature that's going to be negative. So there's a kind of a cooling thing that's happening here. And the demo that I was talking about that you will see another lecture, it's going in the opposite direction. I'm compressing, so as I compress, the temperature rises. And there's heating, and there's enough heating that it ignites the material inside the fire syringe. And here again, there's this relationship between the dynamical quantities in the first law, and we won't really deal with that because it kind of involves too much math. So this graphic in the middle kind of compares the isothermal process and an adiabatic process. So on this PV diagram, you can kind of imagine this curve that looks like 1 over x, or since we are in function of v, this is 1 over v. This is what someone might call an isotherm. This comes from the ideal gas law, which says PV is equal to nkt. And if I imagine solving this for pressure, to get pressure as a function of everything else, that's equal to n, number of molecules, which will usually be constant, times k, Boltzmann constant, a constant, times the temperature. So temperature is a dynamical quantity. It could change, but in case of an isothermal process, temperature is constant through there being so much heat transfer. That divided by V. So when you look at pressure as a function of V curve, that's going to look like 1 over V. That's an isotherm. So between this point and this point, the temperature is the same. So with this comparison, you can see better what's happening, or I guess you can illustrate better what's happening with the adiabatic expansion, for example. The final point is falling below where the other point at the same temperature was. So here the change of temperature is negative. It's going below, so there's some cooling involved. And I can also plot what isobaric and isochoric process looks like. You could have an isobaric expansion. And with the isobaric expansion, I guess the main thing that's driving what's happening is the heat transfer. There's some heat coming in from somewhere, and there's so much heat that one, your system is doing work. All this area under the curve is illustrating how much work is being done. I guess the same as the isothermal process. But in the isothermal process, as you are doing this much work, there was only enough heat transfer to keep the temperature constant, keep it on an isotherm. This isobaric curve, it ends up at a point that's above the isothermal line. So there's an actual positive change of temperature. So this heat input is so large that not only there's enough to power this work that's being done, there's also enough to cause change of internal energy in the positive direction. And there are some realistic thermodynamic processes that we model as an isobaric process. I think that comes up in diesel cycle, which we are not covering. So there must be some source of energy to do that. Isochoric processes are, on this diagram, it's going to look super boring. So for isochoric process, here I'm not even sure what to call it. If it's isochoric cooling, it would have gone down like this. This would have been isochoric cooling, which involves kind of heat being transferred out, so temperature dropping. Or there could have been isochoric heating. That would be at the same point, but going straight up. This would be isochoric heating. Again, some sort of a heat transfer that causes change of temperature that's positive. But moving along this vertical line, there's no work being done. So either way, the amount of work being done is zero. So I think that's all four named thermodynamic processes, and all I can say about them for the time being. Again, this being conceptual physics, we won't do much with these processes in terms of calculation, which is different from physics 4b, where the reason we name these processes is to build up heat engine cycles out of these and analyze them with these different characteristics, helping us do the analysis. But I do think it's good for you to know these names: isobaric, isochoric, isothermal, and adiabatic, and just to know what each of those words mean. Next lecture will demonstrate one of these processes, especially adiabatic, and talk about heat engines in general terms. Thank you. Hi, this is a lecture video on work, internal energy, and thermodynamics. For many of you, especially if you took chemistry, you are already familiar with the ideal gas law, PV equals NKT. Now, the thing with the ideal gas law is, and this is something that surprising number of students forget or neglect, it is a relationship that relates three dynamical quantities together: pressure, volume, and temperature, and usually doesn't change once set. What this means is the ideal gas law actually doesn't say what happens to the temperature when, for example, pressure increases. If volume decreases enough, then temperature can decrease. For some of the thermodynamic processes we looked at, you can quickly figure out how temperature changes. Isothermal process says that the temperature is constant. Simple enough. With the isobaric or isochoric process, since one of the two variables, pressure or volume, remains the same, if the other thing increases, then the temperature must also go up. For example, in an isobaric expansion, the temperature goes up. But what about the other processes, especially the adiabatic process? Since adiabatic means no heat transfer, does it mean the temperature does not change? Surprisingly, the answer is no. Temperature changes in an adiabatic process, and we have to look to thermodynamics to figure out how it changes. Okay, one more piece to go over. From our discussion in chapter 2, section 2.2, temperature is directly related to the internal energy. For monatomic ideal gas, look at section 2.3 for why monatomic versus diatomic makes a difference. A gas of n particles at temperature T has internal energy, microscopic kinetic energy, of 3/2 nkt. So this is where we stand. Say you have a process that doesn't completely tell you everything about pressure and volume, and you are trying to figure out what happens to the temperature. So you're trying to figure out what happens to the internal energy, how the energy is changing. And whenever you see the phrase energy change, I want you to think work. Work gives the change of energy. This is why section 3.2 actually leads with a reformulation of work. In physics 4a, we define the work as force times displacement. Using this model of a piston, you can follow the short derivation to see that for a gas, force times displacement is equal to pressure times change in volume. This is why you are going to be seeing a lot of pressure volume diagrams. It plots complete information about your system. Once you know pressure and volume, you can figure out the temperature from the ideal gas law. And since the total work over a process is pressure as a function of volume integrated over change of volume from V1 to V2. The area under the curve in PV diagram gives the work done by the system in the process. Now I want you to think about adiabatic compression. In an adiabatic compression, the intuitive guess is you are doing work on the system to compress it. So this should increase the internal energy of the system, which increases the temperature of the gas. The first law of thermodynamics is consistent with this intuition. It says formally that change of internal energy can be attributed to two things. Heat transfer into the system is positive, and work done. Work done by the gas is positive, so positive work decreases energy. So for an adiabatic process, 0Q, negative work done on system leads to a positive change in internal energy. Now, the first law of thermodynamics is another relationship with three dynamical quantities. It doesn't say that when gas does work, the internal energy always decreases. For an example, in an isobaric expansion, the gas does work, so that part of contribution is negative. But from the ideal gas law, you know that the temperature of the gas must be increasing in isobaric expansion. Pressure is constant, but volume is increasing. So this means internal energy is increasing. So you have to figure that there must be enough heat flowing in to both do work and increase the internal energy of the gas. Now, for the remainder of this video, let's stick to adiabatic systems since it's simpler, Q is 0, so we only have to worry about work and the change in internal energy. When work is done by gas, expanding under pressure, for example, the internal energy decreases, which means a temperature decrease. When work is done on the gas, being compressed under pressure, for example, then W is negative, so the internal energy increases, which means a temperature increase. I will illustrate this in two ways, with a simulation and with a physical demo. Here is the PHYS simulation states of matter. Let me get some cold sample of neon gas. Here's neon gas at the temperature of 100 Kelvin. As you can see, when I compress this gas, you see the temperature increasing. This is all what we were talking about earlier, but the simulation shows another view, the molecular model view. If you look at this picture of compression carefully, you can figure out from mechanical point of view why the temperature of gas increases. As you can see, these gas molecules are constantly bouncing from the piston. That's what produces pressure. When the piston moves toward the gas molecule that is bouncing off, that's like a baseball bat moving towards a slow-moving baseball that is about to bounce off from the bat. The ball bounces off faster than it came in. So here, if the piston wall is moving toward the gas molecule bounces off faster than it comes in, which means higher kinetic energy and temperature for the gas. This also works the other way. If the piston wall is moving away from the bouncing gas molecule, the gas molecule bounces away slower. Think of a baseball bunt where the hitter deliberately pulls the bat back as the ball bounces in order to make the ball just to drop where it hit the bat. So the gas molecules bouncing from a piston wall moving away cools down. Let me try it here. It doesn't always work well because there are so few collisions. You have to be very careful to move it slowly so that while you are moving it away, the gas molecule bounces off from it. And it doesn't work quite as well. You can try play with it on your own. Um, Now I want to wrap up this video with a physical demo. Well, a recording of a physical demo. This is a piston for illustrating what we have been talking about. I put in a small piece of cotton and push it down as far as I can push it down. And now I'm going to suddenly compress it. See what happens. Ignite. Let me try the second time. Another small piece of cotton. Push it down again. And then I'm going to suddenly compress it again. And it ignites again. This is from the increase in temperature of air, from increase in internal energy of air in the piston, from the work done on the gas in the adiabatic compression. Understanding the ideas you see in this video will help you in analyzing heat engine cycles. Like most other areas of physics, analyzing a thermodynamic process isn't just throwing together equations and formulas you memorize. Like with mechanics, once you have an intuition for the physical processes that take place, it'll help you find an efficient solution path more quickly. That's all for now, and I'll see you in the next video. Bye. I think this is an important thing for someone who's learning thermodynamics to have seen and understood the connection between the mechanical work, which you have seen in chapter 4 and on, and what we describe as thermal energy or internal energy, that there's a direct connection between them. And in fact, the topic of sections 9.8 and 9.10, heat engines, it's that's the device that connects those two. It produces mechanical work from thermal energy. So let me maybe start out with this. Let me start out with the first law. So first law of thermodynamics, it's both what should be actually familiar to you at the basic level of concepts, and it says something interesting. So one is so it's something that you already know. It says so this is the mathematical statement of a first law, that change in internal energy is given by net heat flow, and our sign convention here is a heat flow into the system, minus the work done by the system. So if the system is doing work on the surrounding, that in the physics sign convention, it gets counted as positive. So you subtract the work done by the system. And getting out of that, just the definitions of internal energy, heat, and net work, what this is saying is that whenever you see a change in energy, that change in energy has to be accounted somehow. Change in energy, it could either come from the direct transfer of this particular form of energy
thermal energy or heat, or well, thermal energy, internal energy, or it could come from other way of transferring energy, which is work that you saw in chapter 4 as a way of transferring energy. So so if you think about that, that's what this is saying, that change in energy, it has to be coming from somewhere. Then I hope that reminds you of conservation law that you learned in chapter 4, conservation of energy. And that's really all that first law of thermodynamics is saying. Energy is conserved. I guess maybe what's new here is that we are starting to account for thermal energy explicitly. I think before we were either dealing with the situations where thermal energy didn't play any role, situations where mechanical energy was conserved, or if it wasn't a situation like that, if we are dealing with the friction and whatnot, thermal energy was usually our way of excusing why mechanical energy wasn't conserved. We were just saying, oh, we don't see mechanical energy conserved, but trust us, total energy is conserved. The lost energy just went into thermal energy. That's what we used to do. And with the first law of thermodynamics, we are now explicitly accounting for that thermal energy. Um, so so that's the new part, that we are beginning to account for thermal energy. And what's old, still familiar to you, is that this is just a restatement of conservation of energy. It applies the conservation of energy principle. So um, so this is useful in many different ways. um, I think the most and the demonstration that you saw of adiabatic compression is an example of that. Adiabatic compression is where heat flow is zero, so the work that you're doing on the system, which is a negative work, so minus minus, it's positive change of internal energy. That's what heats up the air. Um, so that's one. But outside of novelty physics demos, or I guess popular camping tools, uh, the way it's important to our modern life is its application to heat engines. And I think I might have said this before. Chapter 9 is quite possibly the single most important chapter in the entire semester, at least when it comes to discussion of public policy and public awareness of scientific things that affect people directly. Because many of us might never deal with electric or magnetic stuff or optical stuff, like all those things. Maybe you are in a job where you deal with those, or maybe you are in a place where you never have to worry about them. But if you use any form of energy, any form of generated power, that comes from heat engines, or most of them comes from heat engines. So, so the way we cover, so like this caption is this kind of summarizing it, beginning with industrial revolution, development of steam engines. Humans have harnessed power through use of the first law of thermodynamics. Um, So it and the electrical power we use today, unless it's coming from solar panels or wind power, um, any kind of fossil fuel or nuclear power, at some point in the power generation, they utilize a heat engine, because a fossil fuel, really the starting place of energy generation, is where they just generate thermal energy by burning fossil fuel. And nuclear power, the way nuclear reactions are used is to heat up water as a way to have thermal energy in a controllable form that can be guided to produce mechanical work. So in this class, we don't get into quite a bit of that detail. I will show you one demo video that will show you some of that detail. But in terms of description of a heat engine, I think the most useful way for us to think of it is more in a schematic way. And this is where first law is applied, Because if you think of a heat engine as a black box, you don't know, we don't have to know exact workings of what's going on in there. But what we do account for, what we do take a look at is in the operation of this heat engine, how much heat do we have to provide? How much work are we able to get out of it? And you will find that for operation of any heat engine, there has to be some waste heat expelled. And engines operate on a cycle in a cyclical fashion. So over a whole cycle, it returns to the same state. And that's the reason it says the change in total internal energy over a cycle is zero. And given that, and conservation of energy, the first law of thermodynamics, the amount of work, mechanical energy that can be provided comes from the difference of the heat flow. So, yeah, I guess it's a schematic description, and it's um, necessarily abstract schematic. I think I've said schematic enough. And this is a more concrete representation of an engine. And I guess this is still somewhat schematic, so it's not specific on, okay, where is this heat input coming from? It depends on the type of engine. So I have a video demo of a Stirling engine. There, the heat input comes from outside. It's just, this piston is hot. That's where the heat is coming from. A lot of the engine that we are familiar with, that if you drive a car, unless you're driving an all electric vehicle, you are driving a heat engine or thing that has a heat engine in it. It uses an internal combustion. So at some point in the engine's cycle, there's a thing that sprays in fuel and air mixture, and there's something that ignites that mixture, and that ignition provides the heat input. So that heat input provides a rise in temperature, which can provide the necessary pressure that gives the force that pushes this out. That's the power stroke. That's providing the mechanical work, and so the power stroke pushes out. That's the work done now, and oh yeah, and this thing has moved to this farther out position now. If this was where we could just stop things, then we could have 100% efficient heat engine. All the heat input here that would somehow go into the work of pushing this out, and you will have 100% efficiency. But we can't leave things there because we don't have one-time use engines. We would like to keep using the engine. We can't just throw it out. So this has to come back to the original position. And this coming back to original position involves moving the piston back. And moving the piston back involves doing work on the system. So this is the return stroke, I think. So in the accounting of the overall net work done by the engine, you have to think about how does the engine return to the original position. So in that return stroke, some work gets done. There's a heat that has to be expelled in order to bring here to the original condition, and then the cycle repeats. That's the operation kind of description of engine. So what rest of the chapter is focused on is something that relates to this waste heat. This is what the caption on the picture above was alluding to, that when people first developed the steam engine, it's not like we had a complete theory of a steam engine and everything that's involved in it. It worked. It was a great invention, but there are details still to be worked out. Are there ways to improve it? Are there ways to make it more efficient? And this waste heat is a source of inefficiency, because the larger this waste heat, the smaller the network produced is. So smart people were trying to figure out, hey, how do we reduce this waste heat? And it turns out there's a fundamental law of nature that prohibits you from completely eliminating the waste heat. You always need to have some waste heat. And that's what, yeah, let me just skip through here. And these are some details of processes that can be used to describe the heat engine cycle. Um, and so there's a law of nature that limits how small you can make the waste heat. Um, that law of nature is the second law of thermodynamics. And this is where there's kind of introduction to reversibility and irreversible processes. And I think all this description of irreversibility in the nature is important to have in mind to fully understand what we mean when we say an engine is ideal. Because when we say engine is ideal, I want you to fully understand that we mean engine made up entirely of reversible processes, not a single, friction that causes irreversible loss of mechanical energy. So, so I want you to have that in mind as we start to discuss ideal heat engines. And now, in that ideal heat engine, um, I think the ideal heat engine that I'm encouraging you to think about is the Carnot heat engine, and I want you to fully understand just how idealized this is. There's no such thing as an actual Carnot engine. It doesn't exist in the real world because the processes that would be necessary to have an actual Carnot cycle, it, Carnot cycle would a real Carnot cycle would take forever to complete. So, so I first want you to understand that when we talk about Carnot engine, we're talking about an idealized theoretical engine. That there's so much idealization that it cannot possibly exist. We are just using it as a tool to explore the limits of efficiency, which we'll get to here. But when you look at this process, so this is what that idealized means. When the engine expands, when it's doing the power stroke, it's moving so slowly so that the engine is always at a constant temperature. It's moving along this isotherm that represents this hot temperature. And the second part of the power stroke, in the adiabatic expansion, this is included because a source of inefficiencies where if the heat transfer takes place, so heat input, we want that to take place at the highest temperature possible. So in this additional expansion, while the temperature is changing, if there's any heat flow, that would limit the amount of efficiency. So in this portion of expansion where there is a change in temperature, we are making sure there's no heat flow so that this expansion occurs without heat flow. And I guess this part isn't that hard to do. You just make things as frictionless as possible. And then after reaching this farthest expanded point, we now have to return the engine to the original point. So we start compressing it. And this compression happens so slowly so that engine is kept at this cold temperature, coldest possible temperature for as long as we can keep it there. And here we want to make sure that this is where you see there has to be some heat that's being expelled, because as you're compressing, in order to keep this at isotherm, you have to expel heat. If we are not expelling heat, then you would be just retracing this adiabatic expansion. So you will just return to the same temperature and you are not back at point A. So this isotherm is where, yeah, you have to expel heat. That's the waste heat. That's going to lead to inefficiency, even in this idealized picture. So once you reach an appropriate point where through adiabatic compression you can return to original point, then this compression finishes up to return you here. And this isothermal contraction is where you have to incur waste heat. This portion cannot be eliminated if you are trying to return the engine back to the original state. So when you take this into consideration and go through the calculation, this is the Carnot efficiency that you end at. And these temperatures has to be in Kelvin temperature, absolute zero scale. And when you think of the typical engine operating conditions, like the cold temperature, let's say you keep it ice cold. That means the cold temperature is 273 Kelvin. Then I hope you begin to see that this fraction is not going to be zero. So the high temperature could be, I don't know, 1000 Kelvin, 2000 Kelvin. If the high point is at 1000 Kelvin, then this fraction will be about one fourth, 0.25. So the efficiency will be 75%. And if it is high temperatures at 2000 Kelvin, then this fraction will now be at, like 10%, 0.1. So the efficiency will be 90%. And as you are thinking of those numerical examples, I hope you see that in order to have 100% efficient engine, just in ideal theoretical world, you need to have either infinitely high temperature, which probably isn't possible. Even the surface of the sun is only 6000 Kelvin. Or you need to have the cold reservoir of 0 Kelvin, which is also going to be quite practically impossible to maintain. So, so in any kind of situation you consider, so for this highly idealized engine, your efficiency will not be 100%. So this is a limitation that heat engines work under, and Carnot cycle quite conclusively demonstrate that, because it is quite literally perfect heat engine. It's a heat engine that can be as perfect as possible, and even then you won't have 100% efficiency. So I think that's all the main points I wanted to touch on. This is quite a long chapter, and there's some bit about second law of thermodynamics that I do get into in Physics Forbidden, and I would have liked to have some time to talk about, which is the statistical interpretation of entropy and second law. This is actually the thing I love about second law, because do I talk about it here? There are many different formulation of second law of thermodynamics in thermodynamics, and the formulation that I don't think it's stated here, so I'll just say it out loud. So under the statistical interpretation of entropy and second law of thermodynamics, you could this is how you could restate the second law. You could say the most likely thing to happen happens most of the time, and that's why disorder increases. I'll just leave that there. All right, let's keep going. Oh, here it is. All right. So, um, yeah, so hopefully you have been reading through chapter 9, and when you got to section 9.9, you've been reading, and kind of what it's covering here makes mostly sense. And I'm trying to keep things simple. So really what you need to know is this basic idea here, that when the heat engines work, it's working through transfer of energy. Energy is still conserved. So heat input comes in as a transfer of heat from the high temperature reservoir, and it could go to two different kind of outputs. One output doing work, and one not really an output, more of a waste, releasing heat into low temperature reservoir. So this is one idea. Let me write that down here, because I have a feeling I'm gonna be needing that. So the amount of work done by heat engine is equal to the difference in the heat flow, heat input from the high temperature reservoir minus the heat expelled into the cold temperature reservoir. And I think I need one more expression. There it is. Definition of efficiency. Let me let me look at the question first. What is it saying? Okay, it's not asking about any like. Oh wait. Let me. So these two expressions are. Yeah, let me just write this one down because this is the most basic definition of efficiency. Um, and this is what we describe as what you want, which is the work, divided by what you pay, which is the heat input you had to provide. So, and in different contexts, efficiency is defined differently. So I do encourage you to read carefully through the textbook sections when it talks about, for example, efficiency or coefficient of performance of a heat pump or refrigerator. There, the considerations are a little bit different. So I think that's all the kind of expressions and ideas you had to know. It says in a single cycle that it takes in this much heat. So that's my heat input, QH, and releases this much heat. That's my heat loss, QC. Also, I just need to take the difference. So 790 minus 330, I think I can do that in my head. That's 460. So 460 joules of work is how much work it does. Okay, and let me just use the definition of efficiency here. I already have the work done, so I just need to divide it by the amount of heat input. So I'll just do that in my calculator. 460 divided by the heat input, 790. And now if I just put in this number, it'll say it's wrong. If I put in 0.58, it'll say it's wrong. And there's a reason, or 583. And the reason for that is it asks for answer in percent. And this is the answer in decimal or fraction. So to get the correct answer in percent, you have to multiply this by 100. I kind of look at the percent symbol as a unit, meaning 0.01. So, okay, so it should be 58.2. All right. Yeah, that's the efficiency of the engine. And one of the things, I guess you'll see it later in the later questions. One of the things that if you understand this about heat engine, you'll have gained a good conceptual understanding of thermodynamics is that you can never achieve 100% efficiency with the heat engines. Not even with the most idealized, frictionless, most perfect engine possible, you cannot get 100%. And that's covered in the context of the second law of thermodynamics. Yeah, I think that this is actually exactly what it's talking about. And here, all you really have to use is the formula for Carnot efficiency. And I mean, I hope you will read through this section and kind of try to make sense of that. For the purpose of homework, really all you need is this. So let me just write that down and just to use it. But I hope you will read through the section and kind of be wonder at what the section is saying, and let me know if some of that doesn't make sense, if you need more explanation. The math here, I guess I don't actually show you the math because it would be complicated math. Okay, so let me just calculate the Carnot efficiency. So automobile, the two operating temperature, the hot is 550 Kelvin, and the low temperature is 300 Kelvin. So let me do this calculation here. 1 minus the ratio of the cold divided by the hot, 550, is equal to 0.455. Now the question wants answer in percent, so let me multiply by 100, and I get 45.5. So 45.5. All right. So automobile engine, even in the most ideal version of the automobile engine, is only about half as 50% efficient. That means a lot of waste heat that has to be there by fundamental laws of physics. Okay, steam, it says the high temperature is 700 Kelvin, low temperature reservoir also on 350 Kelvin. So that's, I guess, a little bit below the boiling temperature of water. All right, let me do the calculation. 1 minus the cold, 350, divided by the hot, 700. Oh, that's going to give me 0.5. Yeah, okay, so that's 50%. All right. And finally, lecture the Stirling engine. Oh, I think I have some video of this. So that's a link from somewhere. Yeah, I think that's a link from one of the essay questions, I think. Take a look at it. It's fun demo. So let me, so high temperature here is 350 Kelvin. So 350, oh yeah, if it's using hot cup of coffee. Yeah, okay, the demonstration that I have is using something hotter than cup of coffee. But anyways, let me go through this calculation. 1 minus the cold, 300, divided by the cup of coffee, 350 Kelvin, and I get 0.143, or in percent terms, that's gonna be equal to 14.3. So that means, basically what this means is there's a lot of heat transferred for how much work is done. So this lecture demo Stirling engine, it does not produce a lot of mechanical work for the amount of heat that has to be transferred. So, all right, so that's all the answers. Do I have more calculation questions? Yeah, you should look that up. All right, I think I did all the calculation questions. So so hopefully all these make sense. If anything is unclear, if you have remaining questions, message me. I will still answer your questions.
And as a treat, here's a video of a working lecture demo of a Stirling engine. Hi, in this video, I want to talk about a topic that I've been hinting at all week: waste heat. I think everyone has some intuitive sense of waste heat because many real world processes involve friction and whatnot. Your computer feels hot when it's on, and when you run, you feel hot. And after driving around for a while, your car engine feels hot. And none of these hotness relate to the working of these processes. Now, the particular kind of waste heat I want to talk about is actually much more fundamental. This is the kind of waste heat that laws of physics themselves dictate must exist. So imagine an ideal, perfect world in which there are no frictions, unless you wanted them to exist, like traction, and no dissipative processes. Even in this world, you'd have this wasted. Let me be a little more concrete. Let's look at a very specific process, a heat engine cycle, the Carnot cycle. It is an idealized, purely theoretical process. No friction enters here. Now, what does it mean for a heat engine to be a heat engine? What is the purpose of a heat engine? The purpose of a heat engine is to turn heat energy into mechanical work. It's to reverse the much more natural process of work turning into heat through friction. So when you look at the Carnot heat engine cycle, through that lens, the only part of the process you want is here, from 1 to 2. Except that would be a very wasteful engine. It's a single-use, disposable engine. The engine starts from 1, reaches point 2, you throw it out, you get another engine at point 1, have it reach 2, then you throw that out. Okay, I'm clearly not being serious here. So the challenge is to bring the engine back to point 1 where it is ready to do work again and do net work over one cycle. If you simply bring the engine back to 1 through the curve 1, 2, then it does no net work. The exact same work done by the engine is done back on the engine, bringing it back to 1. Like a ball bouncing elastically up and down on the floor. This is where some bright person realized if we reduce the temperature of the gas, it'll reduce the pressure of the gas. And compressing the gas in this state will involve doing less work, less area under the PV curve. Then when you're at the right volume, you can raise the temperature back up to state 1 so that the engine can do positive work again. And this area that is enclosed by the loop is what represents net work done. Now, if we had our way, our heat input, the fuel that we had to burn up to generate the high temperature, would all turn into this network. This is what we would call 100% efficient. And in an ideal world, it is really consistent with the first law. Energy is conserved. All of the heat input goes into work done. In fact, that is what happens along this isothermal curve going from 1 to 2. But what you are seeing after this is, because you need to put the engine back into the state you found it, not all of that heat input goes into doing useful work. The work you have to do back on the engine, compressing it from 3 to 4, turns into this heat output along the isothermal curve from 3 to 4. And this is the waste heat. It's the portion of the input heat that must turn back into heat by the end of the heat engine cycle. It's amazing how you can't avoid this, even though nothing in the first law of thermodynamics, conservation of energy, says things must happen this way. It's very tempting to think there must be a loophole here. I think this is what drives the search for the perpetual motion machine sometimes. And this is what I want to emphasize here. This Carnot cycle does represent our best effort at doing this. It's idealized to the point no real-world process can ever be. But you still can't avoid turning a fraction of your input heat into output heat, the waste heat. It's at this point where we say, as physicists, there must be a law that prevents this desirable good thing from happening. And this will be the topic of chapter 4, the second law of thermodynamics. Before I say goodbye, I want to point out one possible loophole. If you spend enough time looking at these isotherms, you come to this conclusion that these isotherms go lower and lower as you go to lower and lower temperature. So if your T2 was 0 Kelvin, then the area under the curve will be 0. And you'll have turned all of the input heat into work. Well, reaching 0 Kelvin is impossible. And making a heat engine operate there is even less possible. But this realization does help develop the intuitive idea of high quality heat and low quality heat. High quality heat energy is associated with larger differences in temperatures. With larger differences in temperatures, greater fraction of heat energy is available to the work. Sometimes this is referred to as free energy. I understand chemists define different kinds of free energy. Low quality heat would be where there's a very little difference in temperature. Sometimes when people talk about heat death, this is what they are referring to. A homogeneous universe where there's no different temperatures between different parts of the universe, and the situation where it is impossible to turn any of the thermal energy into mechanical work. Alright, so on that note, goodbye. Hi, in this short video, I would like to look at an example of a perfect engine. Here the perfect should be in quotes, because what we are going to describe would actually be an impossible engine. So let's start with an example of an engine that somebody already tried to make perfect. That would be the Carnot cycle. You have seen it before. It consists of isothermal expansion, adiabatic expansion, isothermal contraction, and adiabatic contraction. We keep calling this ideal, but you might wonder why. If we refer back to the results we derived, these are the heat transfers and the net work done. It doesn't seem quite perfect to a lot of people for how much heat was inputted. Not all of that heat input goes to work done, and there's a lot of expelled waste heat. That is, of the heat that enters in the isothermal expansion, significant fraction of that has to live in the isothermal contraction. And that seems wasteful. To most people, when you ask them what would be the efficiency of a perfect engine, what they would say is, well, for a perfect engine, it should have perfect efficiency, or 100%. And it's on this measure, the Carnot cycle is seriously lacking in. So let's consider this question. Could we get 100% efficiency by modifying this cycle somehow? When you look at the Carnot cycle carefully, you can see where all this inefficiency is coming from. Look at how much work is done under the isothermal expansion. I'm drawing this slightly off because I'm imagining the whole adiabatic things canceling out. I'm rearranging the shape a little bit. What is causing this to be inefficient is for the contraction back, there has to be so much work done on the gas, taking the heat out. And the area left between two isothermal curves will never equal the input heat, so it'll never be 100% efficient. Now let's dream about changing this Carnot cycle that we know. Here's how I imagine a perfect engine could be built. We could try to avoid all this negative work being done, the work being done on the gas. Let me try this. So we follow the Carnot cycle from A to B, then to C, and instead of returning to D, let's say we are going to reduce the pressure all the way down to 0. Now, practically this would be very difficult, but we are imagining an ideal scenario. Let's call this point E. And now that the pressure is at 0, you can change the volume without doing any work. So there's no work being done here, just the volume changing freely. And once you are at point F, then now you can absorb heat, cause the gas to undergo isochoric heating. Now all of the pink area is the work done, nothing wasted. Now if you look at this carefully, you have to come up with a conclusion. It wasn't so good. In this isochoric cooling, you must be expelling some heat. So it's not true that there was no waste heat expelled. Then maybe you realize at this isochoric heating, there's heat entering your gas. And this must actually be the same amount of heat because you are going back up to the same isotherm. Now, if you are thinking, oh, work done is QH, so it's not 100% efficient, that's not quite right. Because with this modification, in addition to the QH, this amount of Q1 is also an input heat. So it's more like work done is QH plus Q1 minus Q1. And the efficiency actually is the work done, QH, divided by a different denominator, QH plus Q1. Now, you might want to treat it like, but it's the same Q1, don't they cancel out? Well, if you're thinking of the normal perfect engine, these two Q1s are different. Kinda oversimplifying here. The Q1 being released here has to go into the low temperature reservoir, the one at 0 Kelvin. And the heat that's entering here has to come from the high temperature reservoir, maybe one at TL. So that's the sense in which these two heat are different. They are not coming to and from the same reservoir. If you really want 100% efficient engine, then this is what you need. Instead of this heat here being released into lower temperature reservoir, you need to be able to release this heat into TL. Then these two Q1s will now truly cancel. They are truly equivalent to each other. The minus Q1 here cancels out the plus Q1 here. Now, unfortunately, this process here is what is forbidden by the Clausius statement of the second law of thermodynamics. Heat never spontaneously flows from low temperature to high temperature. This is one illustration of why Clausius statement is equivalent to the Kelvin statement. Because if you could imagine, he could possibly flow from low temperature to high temperature, then that's all we need to make a 100% efficient, perfect engine. But that's not true, so we can't make a 100% perfect engine. Instead, we are going to have to be limited by the efficiency of a perfect engine that's allowed within the laws of thermodynamics. That's the efficiency of the Carnot engine, or taking the ratio of the work and the heat input we see there. A lot of numbers cancel out. You get TH minus TL over TH, or equal to 1 minus TL over TH. This is the maximum possible efficiency given access to two thermal reservoirs, the lowest possible temperature TL and the highest possible temperature TH. Any other reversible cycle or irreversible cycle operating within this regime wastes some of the possible efficiency. It's the Carnot cycle that makes sure that all heat input occurs along the highest possible temperature and that all heat output occurs along the lowest possible temperature. So we are going to have to resign ourselves to that. The Carnot efficiency, which is never at 100% unless you have access to 0 Kelvin low temperature reservoir, is the most perfect engine possible. We are going to soon look at the second law of thermodynamics through a different lens, and in this different lens, Carnot cycle will be useful again, although not in such a quite unique role. Until then, Bye. Hi, this is a lecture video on disorder, entropy, and second law. So you have seen second law stated in a few different ways. The Clausius statement, the Kelvin statement, and finally, statement based on change of new quantity called entropy. Now, for those of you who intend to major in physics, I hope you have this sense that all this is very interesting and deeply unsatisfactory. This is what I mean. These all three ways of stating the second law of thermodynamics seem to be related. But why should they be? And if they are related, and you can kind of show why, which of these three statements is the most fundamental? We call physics the fundamental science, and it's not just the physicists being pompous. We do actually seek to explain the laws of nature in the most fundamental way possible. And these three ways of describing the second law are unsatisfactory because they are phenomenological descriptions. What it means is it's based on phenomenon. As in, we are trying to describe the experimental observations. Not based on first principles, but based on trying to explain what you see. In fact, the way we introduce the change of entropy is an example of that. And this is kind of why later on we had to qualify that this only applies to reversible processes. Because that's the phenomenon we used to come up with it, and we realized when we tried to apply to irreversible processes, non-quasi-static processes, that it didn't work. So for especially those of you intending to major in physics, if you have that feeling of dissatisfaction, then your heart is in the right place. Now, there's a second feature of the second law that begs for an explanation. Some textbooks refer to it poetically as arrow of time. What it means is the second law is the only law that says something about flow of time. It refers to irreversible processes. If you go back and look at all the other laws of physics that we have covered, including the first law of thermodynamics, you'll find that they are all reversible. They hold when you reverse the direction of time. It's true for conservation laws, for obvious reasons. It deals with equality. It also holds for things like Newton's laws. So, second law is special, and this raises the question, why is the second law special? It's these questions that I'm hoping to answer in this lecture. Now, the challenge with the thermodynamics is that the system we are trying to describe is too complex. In physics, we are not used to dealing with the 10 to 20, 10 to 30 particles. In upper division statistical mechanics, you are going to develop tools that can be used to analyze these systems. But for the purpose of this class, let me use a toy model to illustrate the ideas without getting too deep into the mathematical analysis. So this is going to be our system. We are going to have 25 coins that can have heads and tails. Let me get 25 of these. Alright, there are 25 coins nicely lined up. Let me give them coordinates so that I have some way of referring to them. So, for example, if I wanted to refer to this coin here, I would refer to coin 4, 3. Alright, now what I want to illustrate here is how random process will inevitably lead this system from order to disorder. So let me start out with the most ordered possible version of this system. All heads. Without going into complicated mathematical detail, it intuitively feels ordered, right? Now, I need to introduce some random process. And for that, I wrote a little Python function. So in this little Python script, I have a list that's a list of these coordinates of 25 coins. And Python has a function that I can use to take a sample of 5 out of this list at random. And I'm going to use this to choose 5 coins to flip each time. Each time its number comes up, it gets toggled from head to tail, tail to head. We'll go through a few iterations of this and let's see what we end up with. Oh, I can use this as the first iteration. Let me flip those coins. Alright, replace those coins with the tail version. Second round. Replace them one by one with their other version. You can flip back and forth in the video if you want to make sure I'm not cheating. Okay, another cycle. Alright, double check it's right. One more cycle. Alright, keep going. One more cycle. Alright, I don't have all day, so let me do it 2 more times and then we'll call it a day, see what we have, and we'll talk over that. So, one more. And now the last one. Alright, let's call it a day. Let's do the tally of what we have. We'll just count the number of heads and tails. So, counting the number of heads. 1, 2, I'll count silently. 13, 14, 14. Counting the number of tails. 1, 2, 10, 11, 11. And they add up to 25, just a quick checksum. It's a curious statistical fact that random process wasn't trying to enforce some 50-50 ratio of heads and tail. I was just picking some coins at random to flip. And if we were to continue this process indefinitely, you would find that the number of heads and tail fluctuate around about half. And it's this phenomenon that we are referring to when we say that the state of a system tends to disorder. I guess you could consider this another statement of second law. And you might have heard of entropy being described as a measure of disorder. So I hope this example with 25 coins gives you some intuition for how a state starting with a perfectly ordered system tends toward disorder with the introduction of random processes. And it doesn't seem to go the other way, even though nothing in the setup of these coins prevents all of the coins somehow being flipped to all head again, or to all tails. We can explain this with ideas from combinatorics and the idea of microstates and macrostates, but 25 coins are too many. Let me reduce the number down to 4 and we'll talk about it. So with 4 coins, it becomes possible to list every state of the system. From combinatorics, with 4 places and 2 states possible for each place, you have the number of possible states figured out this way. You take number of possibilities for each place raised to power of number of places. So this is 16. Still kind of large, but not as large as it would have been if it was raised to 25th power. Alright, so let me just list them all. I gotta make these coins smaller if I'm gonna fit them. They are being grouped in some kind of fashion if you can figure it out. Almost there. And that's the last one. Let me make sure that I have 16. 1, 5, 11, 16. And that I don't have any duplicates. Alright, so this is the complete listing of all possible states of a 4-coin system. And I hope you figured out how I was organizing them. Each of them are grouped by sharing the same number of heads and tails. You could almost think of one almost as being the bird's eye view, or the forest, and the other one as being the trees. We introduce a new vocabulary to describe this. The states shown on top are called microstates, and the states shown on the bottom are the macrostates. All the descriptions of thermodynamic systems we have been using so far are the descriptions of macrostates. You can kind of see that because the macrostates are characterized by the average quantities or the aggregate quantities. And that's a good description of temperature relating to average kinetic energy, and pressure and maybe volume relating to the aggregate quantities. And what we are positing in the statistical mechanics is that for each of these macrostates, there's an underlying microstate that can correspond to the macrostate. In fact, here there's 6 different versions. And here's a canonical assumption that you will hear in statistical mechanics, is that each microstate is equally likely. I hope that makes intuitive sense. It's like when you have a 6-sided dice, you throw it, you have an equal chance of getting 1 or 6. Or any other number in between, 1 in 6 chance. So what this statement is saying is given 16 possible microstates, you have 1 in 16 chance of getting any one of them. And given this assumption of equality, the natural question is, why are macrostates so unequal? As you saw in the previous example, with the introduction of random process, I don't have equal chance of getting all heads as getting half heads and half tail. And this figure is an explanation of why. Some macrostates contain in themselves more microstates. There's 6 that can lead to 2 heads, 2 tail possibility. But there's only 1 microstate that can lead to all head possibility. If you go through math, what you will quickly find is that as the number of particles increase, this disparity becomes much more extreme. So here, with only 4 coins, the even distribution is only 6 times more likely than all heads or all tails possibility. But as your textbook lists, even with 100 coins, which is reaching nowhere near the statistical systems we deal with, something like 10 to 10, 10 to 20 number of particles. The difference between the number of microstates in the macrostate representing the sort of even distribution, and the number of microstates in the macrostate representing a very skewed result, like all of the gas molecules being collected into a corner of a room, becomes extreme. This is why if you took 4 coins and flipped them all in the air, it is most likely for you to get 2 heads and 2 tails. Now with only 4 coins, you have a fairly significant probability of getting maybe 3 heads and 1 tail. 4 in 16 chance is nothing to sniff at. Now getting all heads, that is less likely, 1 in 16, but this is what 1 in 16 means. It means if you did that experiment 16 times, you have a decent shot of getting it once. So this is the mathematical fact, statistical fact, that's underlying description of anything, from the toy model that we've been talking about to the real world system of ideal gas. And all these different statements of second law, what we've been talking about so far, what they are really saying is they are describing how when you start from a macro state that is quite unlikely, and it goes through some random process or stochastic process, then it is mostly likely to land on the macro state with the most number of microstates because it's most likely. This leads to the statement of second law that is my favorite version of second law. So let me give that statement and leave it there. My most favorite statement of second law says this: What is most likely to happen? Happens most of the time. Those of you who go on to study statistical mechanics in upper division, this describes mostly chemistry and physics majors, you will get a chance to see what we mean by this statement.